So, hello. Today we are going to do some quick review of some explainable AI methods. Let's first review the methods of model interpretability. This is one of the papers that systematically describes the criteria for interpreting the models. And basically, a model needs to be transparent and have the post hoc interpretability. For transparency, this paper means that human can contemplate the entire model at once, so we can think about the mechanism of that model, or in other words, we should understand the how this model is constructed easily, and this implies that we should use easier models instead of the very complicated ones. But simulatability is a very subjective criteria, and same as decomposability and algorithmic transparency. So for decomposability, this rule means that each part of the model adopts the same explanation. And the explanation here has vague definitions. People in the future will give this explanation very different explanations. And for algorithmic transparency, this basically means simulating as simulatability. And for the other set of criteria, post hoc interpretability, this means that we should be able to give some explanations to the models after the model makes its predictions. And the post hoc interpretations will allow us to explain what this model has done. These approaches could include text or visual explanations, local explanations, or explain by example. There are also some possible counter arguments. So for transparency, linear or simpler models are more transparent, and the transparency requirements might be against the model performances. And post hoc interpretability, these are simplified interpretations and might be misleading because we are attaching another set of predictions based on the performances of the more complicated models. And it doesn't guarantee us that the new explanations, although they might be more simple and easier to understand, that they might not be as accurate as the original predictions. And also there might also be the problem of amplifying the bias or the surface shortcuts. So in today's talk, I'll review some popular interpretability methods, including the local linear model agnostic explanations, Shapley additive explanations, attention-based explanations, and CCA. So let's first get to line. So the ideas follow the previous arguments of Lipton. Linear models are interpretable. These are almost the most simple category of models. And another assumption is that complex high-performance models are almost linear locally. This resembles the sort of first-order terms of the Taylor expansion. No matter how complicated the functions are, if we decompose them, then only take the first order term. The first order term is always linear, and second order terms, if we are figuring out, if we are decomposing the terms at points that are at some suitable places, then the higher order terms are smaller than the linear order terms. So it seems possible to fit the model locally. So their method is, in order to explain a model F, they plan to find a model G that minimizes the loss function. And this loss function is composed of two parts. L is the accuracy term. They compute the accuracy of the model G based on F, and also a proximity measure, for example, L2 distance. So this term, the L term, tries to minimize the prediction between the explanations to the original model. And they also add a complexity penalty term, omega of G. This limits the complexity of the explanation model. So by minimizing the sum of these two loss terms, they try to find an explainer model G that is simple and linear, and almost linear locally. So this is an illustration of the model. So although the overall model F, the orange one, is complicated, we can find some local linear explanation around some points that we want to explain. So the dotted line is the linear explanation, and this linear explanation works locally but not globally. So we do not need to be restricted to the local linear model. And there are many other types of additive linear models. And for example, we can approximate them. This is a more general explanation. And if we have the data points, which are Z1 all the way to Zn, and each of the data point, or each dimension of the data point has a feature weight phi I, and we can use this the vector of phi to explain the importance of these features, and to construct this G using this phi and the data point Z. This is an additive linear model explanation. So one of the methods to compute the feature importance phi is to use the Shipley value. So the Shipley value is an algorithm that comes from the game theory. The overall idea is that there are many features in total. There are many possible combinations of these features. And what if we look at the average effect of these features with this feature I, and the effect that we take up all the possible combination of the features without this feature I. So we take their differences and average across all possible choices. Then the result will be the expected importance of this feature I. This is the Shipley value of the ith feature. So the equation is like this. So f of the feature set with the ith feature minus the prediction of this feature set without this feature, and we take this average across all possible combinations of of the feature set S. So this is basically select S from F features and then average them. So this becomes the expected importance of feature I.
Yeah, sorry, I have a question.
Yeah.
So what is output of F? So your input is a data set, but I think they have different numbers, the first term and second.
Yes.
But how do you compare the difference between two?
The output is just a scalar. So F is it's like it's a predictor model, and the input are a vector, and in this case the input is let's say if we say S is a feature set of 5 features, then here F is a mapping from 6 dimensions to 1 dimension, and this F is from 5 mapping from 5 dimensions to 1 dimension. And
Oh, I see. So
yeah, and it seems like this there should be different models. So there are, and I think for each combination of the models, there should be one. Sorry, for each combination of features, there should be one model, and the model should be.
yeah,
but the model should be trained fast. I think this can be linear models or something like that.
Yeah, but should we calculate the expected value of this term instead of on a single data point?
The expectation of the expectation is taken across the choice of S features. So for each S features, we take the difference between S plus feature I predictive power and the feature S predictive power.
Yeah. So yeah, I understand S is referred to a subset of features,
Yeah.
but here phi I refer to the importance of the I's feature.
Yeah.
It's calculated by using one single data point, which is X. But should we like do something like expect value of this term? So, for example, we have a set of data points and calculate the mean of this term, the expected value of this term.
I think when they train F using this subset of features, they are implicitly taking the average of all the data points that are considered, I guess.
Okay.
Yeah, they're averaged here as well. Okay, cool. So for the attention-based explanations, initially the attentions was introduced in the sequence-to-sequence translation models because the original authors are afraid that just by cramming everything into one vector into sequence-to-sequence model might not be very efficient, and the compression rate might be too large, and they're afraid of some lost information. So they just set up some attentions to transfer, like to carry more information from the source to the target. And later they are widely used for other places. For example, the self-attention, because attention is essentially just additional connections. And if you connect them in some efficient and well-designed ways, the models could be very performative. Like attention is all you need paper. This transformer model is almost taking the it's almost replacing LSTM in the NLP classification tasks, but we will talk about that later. And more about the attention-based explanations can be seen at this block. And there are some methods to try to interpret the attentions. The attention, as its name suggests, has some potentials for interpretability because they are they have some correspondence to some specific features in the input. So if some positions attentions are highly activated but not the remaining positions, then this indicates that a few positions might be important. And this paper analyzes this assumption using a flat attention network. This is a very, very shallow network, and by looking at this network, it's easier to analyze the correlations. And they apply this model to the text-based classification like Yahoo, IMDb, Amazon, and Yelp. So the first thing they do is to single out the importance of each attention. So they mask one position in attention and see what happens. So if the overall Jensen-Shannon divergence is large, then this position of attention might be more important. And the attention magnitude seems correlated to Jensen-Shannon divergence. And then also measure how many of the model's decisions are flipped. So if you mask the attentions with larger attention magnitude, they observe more flips in the eventual predictions of the model. And they also attempt to find a set of important attentions. They rank the attentions by heuristics and mask them starting from the least importance and see how, during this process, do they flip the model predictions. So when they use the attention weights as heuristics, and they also use the representation values or saliency scores, and they observed slightly different sequences of flipping the model predictions, and the results are in the original paper. I pasted the link here. So overall, they found the attentions are noisy predictions to the input words importances. And there are also two relevant papers. The attention is not explanation. This paper claims that the attention weights are uncorrelated with the gradient-based measures of feature importance. And a few months later, the attention is not non-explanation paper claims that the above paper allows too much flexibility in the analysis. So these are the attention by interpretation by attention methods. Now let's talk about the explain with CCA. So canonical correlation analysis was originally used in multi-view learning. So given two matrices X and Y, the goal is to find two vectors A and B that can minimize the correlations between AX and BY. So A and B projects the data set X and Y to some common spaces as common as possible, and they want to minimize the distance between the projected matrices. So later, if they replace the vectors A and B to some neural models like F1 and F2, then this becomes deep canonical correlation analysis instead of the CCA. So the CCA or deep CCA finds a common view, and more importantly, this gives us a measurement of how hard it is to find this common view. So if X is a norm model, then we can explain Y with X. And by measuring how different is this model with the unknown model Y, then we can somewhat approximate that on, for example, on which layer this model is, this deep learning model is the most similar to for example, syntactic parser. And SVCT is an additional step before the deep CCA. So because deep CCA requires operating on smaller dimensions, and they can use an SVD to go from the high dimensions like 1000 or 2000 in LSTM to the low dimensions like 10 or 20, and then they can do CCA very fast. So there are many possible applications for that. Like the E-model comparison, they can compare between different layers or components. And inter-model comparison, this is what I mentioned just now. You can compare a deep learning model to a non-model like syntactic parser. And the syntactic parser can also be an LSTM as well, but we know that the syntactic parser is extracting the syntax. And they can compare the different layers between these two models. Okay, here's a more recent paper. This is a survey of explainability techniques for text classification. There are attribution maps, which is almost similar to the explained by attention category. They are this includes, for example, agreements with human rationales, confidence indication, faithfulness, rationale consistency, and data type consistency. And gradient-based approaches like saliency. So saliency is the gradient score of the each locations. And perturbation-based approaches, occlusion. Like if they mask some features, what will the output turn into? And there are also some other words saying that instead of masking, you should replace them with some random words, or you should replace the positions with some tokens that are not occurring in your neighborhood. And there are a lot of different types of perturbations. There are also simplification-based explanations, for example, line. And for faithfulness, this paper discusses about the definitions for faithfulness. So the authors claimed that it's very hard to, so it is very easy to confuse plausibility and faithfulness. So plausibility means how convincing this interpretation is to humans, and faithfulness means how accurately it predicts the model's reasoning process. So the current definitions of this one has two assumptions. Same reasoning process leads to the same predictions, and similar reasoning indicates similar decision given input. So this makes sense, and the third assumption, some parts of the input are more important than others. I'm not very convinced by that, but this seems like an assumption that the faithfulness needs to have. So, okay, and this is an interesting work. So this this paper analyzes how humans actually benefit from interpretability, and whether humans are really affected by the interpretable models, and they analyzes the behavior of real human from the model predictions. They give human they recruited like 2,000 humans and let them to predict the apartment selling price from the features, and they also let them different models to do, and the models contain 2 features of 8 features model, and each of the selection of models contain the black box version or the white box version. So in black box version, the humans are able to see the model's reasoning process. Sorry, black box humans are not able to see, but the white version, white box version, the humans are able to see the weight of the models. And both humans and the models predict the selling price from the 3 features. The first experiment is that let the participants guess how much the models will predict, and then show them the model predictions, then guess again. So, and the second experiment is to scale down the selling price and replicate this. And the third is to use some weight of advice to measure how much people follow the model's predictions. So basically, the participants did not follow the model's predictions, and the participants did not correct the model's sizable mistakes. This is interesting, since an interpretation of these results are that the interpretability does not benefit the human, and a human basically did not listen to the model's predictions. And when the models make some mistakes that are, in other words, the models predicted selling price is very different from the true selling price, the participants didn't realize that. So they added 2 additional experiments. The fourth experiment is still the E1 setting, but they were shown a signal. So this apartment may be an outlier. So the finding is that when shown this signal, the participants can detect and correct the model mistakes. So it appears as if this signal, instead of the model's predictions, are allowing the participants to detect the outliers of the models. And the fifth experiment is a post-hoc analysis for E1 and E2. The participants shown clear 8-feature model follows the predictions less closely than clear 2, black box 2, and black box 8 models. So it seems like the two features models are better than the 8-feature models in allowing the participants to follow. And specifically, the clear 8-feature model. So the white box 8-feature model gives the participants an information overloading. So this could be and sort of an inspiration for us to design the explainer model. So we shouldn't give too many features to the humans to explain something. This makes sense because if there are too many features, then the humans might just say too long, didn't read. So to avoid the information overload is an important thing to make some interpretations of the models useful for humans. So as a summary, we reviewed some principles of model interpretability and reviewed some early methods to interpret the models, including local, linear post hoc methods, line, and a method based on Shipley values, and attention-based models, and SVCT. There are also some many recent methods. And we also talked about the indications of interpretability for human in a study involving the 2,000 humans. So there are also some more recent models. We'll discuss them in upcoming weeks. Thanks.